All right, so finishing up where we left off yesterday for f, remember the degree of the numerator was 2 and the degree of the denominator was 3. So because the degree of that numerator was less than the degree of the denominator, what did we say the limit was going to be?
0.
Yep. And I think, well, I can't remember if I gave you a helpful hint, but remember that this one, the degree of the numerator of 1 is what? What's the degree of 1? The number 1, 0. And what's the degree of n? 1. So isn't the degree of the numerator here smaller than the degree of the denominator here? What was the limit on 1 over n from yesterday? What was the limit of 1 over n? 0. So it makes sense that when, I mean, this is one that's easy to remember. 1 over n, you can always think 1/2, 1/3, 1/4, 1/5. Oh yeah, it gets closer and closer to 0. That'll help you remember that when the degree of the numerator is smaller than the degree of the denominator, that limit is 0. Again, that was a horizontal asymptote rule. If you were to graph this on your calculator, so go ahead and graph it on your calculator if you have your calculator with you, and you will see that there's a horizontal asymptote at the x-axis, which is where y is 0. And as n approaches infinity, the value of y is approaching 0. And so we would write this as the limit as n approaches infinity of 5n squared over n cubed plus 1 is equal to 0. Since the limit is an actual finite number, does this converge or diverge? It converges. So it converges to 0. Then look at the last one on this first page, G. What is the degree of the numerator? 3. And the degree of the denominator? 2. So this time the degree of the numerator is greater than the degree of the denominator. So when this happens, the limit is equal to infinity. The horizontal asymptote rule for this one was that there was no horizontal asymptote, but there might have been a slant asymptote. So if you go ahead and graph this on your calculator, I'll put a brief sketch up here. It's going to look like this. It has some little squiggle down here, and then it comes up like this. So you can see on your calculator, see this slant asymptote coming through here? As n approaches positive infinity, what's happening to the value of y as n gets bigger and bigger and bigger? Y gets bigger and bigger and bigger. Isaac, we're going to have to talk about that bathroom break. That was a really long one. Like incredibly long. It was 20 minutes long. That'll never happen again. So the fact that the limit when the degree of the numerator is bigger than the degree of the denominator is infinity will always occur. So written, the limit as n approaches infinity of n cubed plus 2 all divided by n squared plus n is equal to infinity. So does this sequence, does it converge or diverge? It diverges. And if you recall, it does not diverge to a number, it just diverges. So any questions about that front page that we talked about yesterday? Hopefully you started your homework. It's a really big hope, I know. All right, so let's look at the back. So page 2. So today we're going to look at arithmetic sequences and geometric sequences and how to write them explicitly and recursively. So I will give you all the formulas on this page. I don't have a problem doing that. I'm not going to make you memorize all the formulas. Don't forget that arithmetic sequence is a sequence that has a common difference. And I don't particularly like, well, on this one, I don't particularly like the formula for the explicit. Like, for instance, when you're finding C, you have to know that C is equal to A sub 1 minus D. I prefer to use instead the following formula. A sub n, and you'll see me using this, is equal to A sub 1 plus n minus 1 times D. That's one I prefer to use, and I don't have to worry about C. But sometimes, you know, this one's helpful, and I'll give you both of these, but sometimes this one's helpful if you have a formula in this form. Then you could find your A sub 1 because you would know that D is here. And you could find your A sub 1 this way in case you had to. So you might run into a problem where you need to use that formula. But for this one, we're going to find a recursive rule, and we're going to find an explicit rule for each one of these. And so looking at this one, I've got to gather the information that I need. So for my explicit rule, I need A sub 1, I need n, and I need my, well, I don't actually need n, because we're going to keep that n there. We're going to find the general rule. So all I need is my common difference and my A sub n. So what is my common difference? What's happening from here to here, from here to here, here to here? Yep, so we're getting bigger by 4 each time. So your common difference is equal to 4. Sometimes your common difference is negative, so be really careful with the negative ones. And then our A sub n is this number right here. So our A sub 1 is equal to negative 6. So I'm going to use the second formula. So I've got A sub n is equal to my negative 6 plus n minus 1. And then I always put my common difference in parentheses. If you don't get in that habit, when your common difference is negative, it's going to look like a subtraction problem. And then you need to simplify. So we're going to distribute that 4. So we get negative 6 plus 4n minus 4. And then finally, our rule for A sub n is 4n. The negative 6 and the negative 4 gives you negative 10. And so this is explicit. So you do need to simplify it. Then the recursive rule is pretty simple. If you look at the recursive rule, we're just taking this A sub n minus 1 stays the same, that doesn't change. We're just adding the common difference to this. We're replacing D with a common difference. That's it. So your recursive rule is simple. A sub n is equal to A sub n minus 1, and then in this case our common difference is 4, so it's just plus 4.
Wait, is this for part B or is it already solved part B?
This is still A, because they wanted the explicit and they wanted the recursive, so this is our recursive. Bless you. Because you have to have 2 parts to that. Any questions on that? All right, so you're going to do B by yourself. And I'm going to do it quietly here without... Oh, would you mind handing me that? Thank you. Nurse passes. You're a funny one. So find both rules the recursive and the explicit. And then when you get an answer, share, share, share. Uh-huh.
Are you just not supposed to find what n equals?
No, because you're just finding the general rule.
Oh.
So that if you had to find the other values in the sequence, like if I asked you to find the 150th value, or the 150th term in the sequence, you could plug it into that formula.
Oh.
All right, so here's your answers up here. Your explicit was, listen, your explicit was 2n plus 1, and you do have to have the a sub n as part of that. It's an equation. And then your recursive is a sub n is equal to a sub n minus 1 plus 2. Any issues, problems, or concerns with that? You should find today's lesson pretty simple. All right. What was that? Oh, you messed up. What'd you mess up on?
On the explicit part, I got the recursive. I just.
Oh, gotcha.
I didn't put the n minus 1. I'm just. I don't know.
Were you using the
I don't
dn
remember
plus
this.
c one?
Huh?
Were you using the dn plus c one?
I honestly don't know.
Okay. Does this make sense what I put up here?
Yeah, now.
Okay.
I don't know. I just don't remember learning this. I'm learning slowly.
You did in Algebra 1 too. What did you have in Algebra 1 too?
Oh yeah.
I know. I know I taught that to you.
Does
What's
it
up?
matter if you have the 2n first?
Oh, you mean if you put the 1 plus 2n?
Yeah.
No, that doesn't matter. I tend to write it because arithmetic tends to be linear. I tend to write it in y equals mx plus b.
But like you won't be marked off on a test for
No. No. All right, so any other concerns? We good? All right, so let's look at the geometric sequence. So for your geometric sequence, sequence, they have a common ratio. And that common ratio, R, is your common ratio. Be careful when you find the common ratio when you're just looking at a sequence like this, that you don't say that the common ratio, well, let's say that the sequence went backwards. If the sequence went backwards, 81, 27, 9, 3, ... Oftentimes I'll have kids tell me that the common ratio for that is 3. Or they'll say divided by 3. The common ratio is always in terms of multiplication. So in this particular instance here, instead of dividing by 3, what would you have said? Times 1/3. So you always have to look at the common ratio as if it's a multiplication problem and not a division problem. So here, always to find your common difference, this right here is just telling you, take the previous term and put it, take the term on the right and put it over the term on the left. So if I look at, for instance, these two terms right here, the term on the right is 9, the term on the left is 3. So my common ratio ends up being 3. And you're going to see here that there are some common ratios that are different. And then we have some formulas. So we have an explicit formula, and we have the recursive formula. And this is going to be really important to when we talk about 9-4 today, but in the explicit formula, notice that the number that's in front of this base being raised to the n minus 1, this number that's in front that will look like a coefficient is always the first term. And then whatever base is being raised to the n minus 1 is always your common ratio. So it's easy to find, and it's easy to tell when you're looking at a function or a rule, whether it's geometric or arithmetic. Geometric will always have something raised to an n minus 1. It's easy to see. So then look at this right here. We're going to find both a recursive rule and an explicit rule. So in order to do that, I need to know a sub 1 and r. So a sub 1 is this term right here. So a sub 1 is equal to 6. How do I find r? Or what is r? Yep, so I'm going to take the 6 and the 12, and I'm going to take 12 and divide it by 6, so my r is 2. And that's all I need for my explicit. I'm going to start with explicit. So I have a sub n is equal to 6, because that's my a sub 1, times my r, which in this case is 2, and that's raised to the n minus 1. I like to put that in parentheses though, because especially if your common ratio is a negative, you don't want to leave it out of parentheses, because you're raising that negative and whatever the number is to that n minus 1. It has to be in parentheses if that r is negative. So you might as well just get in the habit of putting in parentheses all the time. And so that's it. This is your explicit rule. I can't simplify that rule any further than what it is. And then for your recursive rule, a sub n is equal to the a sub n minus 1 doesn't change, and then you're just multiplying it by your common ratio 2. Do you think Math Excel is going to accept that as an answer?
No.
They probably won't. And it's like nails on a chalkboard to me. That really needs to come in front. And so your actual final answer for the recursive should be 2 times a sub n minus 1.
I don't want to trust you with that joke.
I would, yeah. Makes your teacher a whole lot happier. All right, so I would let you do B on your own, but with the base 10s, it gets a little complicated. So let's talk about what we have. So let's find our a sub 1, which is our first term. So a sub 1 is equal to 10 to the negative 3. And if you have a sequence like this that is written as powers, a base to an exponent, you want to keep them in powers as long as possible until the very end. Otherwise, it's going to mess up your final answer. And then to find our r, what am I going to do? What do you put over what? I would take these two. So I'm going to take 10 to the negative 1 because it's on the right, and put it over 10 to the negative 3. There's a lot of exponent rules in this problem. When you are dividing like bases, what happens with the exponents? Do we add, subtract, or multiply? You subtract. So all of this, I am subtracting a negative 3. Because you're subtracting, so you're subtracting that negative 3. And then r equals 10 to the negative 1 plus 3, so isn't that 10 squared? Negative 1 plus a positive 3 is 10 squared. Right?
Yeah.
You're going to take right here and make those plus plus. So that's how you get the 2.
Wait, how do you get the plus plus?
Because we took this and subtracted the negative 3. So it has to be
right.
minus and minus, right? And so the minus minus changes to a plus plus. And then don't change this to 100. I know that it's screaming out at you to change it to 100. Don't do it yet. All right, so then we're going to get our explicit rule. So a sub n is equal to a sub 1, which is 10 to the negative 3, times, and then we have 10 squared raised to the n minus 1. Well, we have a power to a power, don't we? Power to a power. What do you do with exponents on a power to a power? You multiply. So this ends up being equals 10 to the negative 3 times 10 to the 2 times, and maybe I'll make that 2 red. Oops. No, maybe I won't. Never mind. It's not going to let me. And so then I want to distribute that 2, and so I end up with 10 to the negative 3 times 10 to the 2n minus 2. I'm still not done because I have the same bases. So when I have the same bases and I'm multiplying like bases, what do you do with these exponents? You end up adding them. And so we're going to take this up here to the top. And this equals 10 to the negative 3 plus 2n minus 2. And so finally, a sub n is equal to 10 to the 2n minus 5. Ugly but true. So all of that is your explicit. That was fun, wasn't it? All right, the recursive is much easier. Are you okay if I take the r and put it immediately in front of the a to the n minus 1? All right, so on the recursive, we've got a sub n is equal to, we have 10 squared times a to the n minus 1. MathXL will probably not accept that as an answer because you can actually raise 10 to the second power. So a sub n is equal to 100 times a sub n minus 1. And that is your recursive. And then we have just one last item to look at after you get that written down. We good? All right, so we're looking at recursive sequences here. Recursive sequences, as we learned yesterday, it's defined using the previous terms. So you usually have to be given at least the first term, if not the first two terms. Well, this is a really special sequence right here, Fibonacci sequence. It's 1, 1, 2, 3, 5, 8, and then it keeps going. This is a phenomenal sequence. Can anybody tell how you find the next terms? You do what? How would you describe that in general? Take the previous, you take the first two previous terms, right? So, in other words, you have to take 1 plus 1, oops, I missed it a little bit, gives you the 2. And then the 1 plus 2 gives you the 3. And then the 2 plus 3 gives you the 5, and so forth. So it's always the previous two terms gives you the next term. Well, what's fascinating about the Fibonacci sequence is that you see it in nature over and over and over again. It's just unbelievable. You know, and a simple example would be, look at a pine cone or a pineapple. They both have identical kind of spiraling, whatever you want to call those prong things that go around the pineapple or the pine cone, right? If you look at the very end of it, it starts with 1, and it has another 1, and it goes to 2, and then 3, and then 5, and so forth. And then you can see that on petals on a flower. Look at a sunflower. It's fascinating. What's more fascinating is who had the time to figure that out? Fibonacci. All right, so any questions on that? Are we good? Okay.